All right, everyone. Today, this is our class number 22. We're going to go over the boosting algorithm, namely AdaBoost, actually the very basic version. And then we'll be talking about gradient boosting machines, GBM, and then XGBoost. We will slightly talk about the latest models out there. For example, Microsoft released the Light GBM back in 2017, January. And then there's this cat boost that Yannick's, I believe. It's a leading tech company in Russia. They open source the cat boost. I'm going to talk about the very latest models out there. But in many competitions out there, XGBoost is the model in the realm of supervised machine learning, right? It's the winner. There's a reason that's the winner. And we're going to be discussing why we will prefer XGBoost to any kind of other machine learning models. And sometimes why not, right? So we have to be careful that sometimes it's not necessarily the best option to use XGBoost. Okay. All right. So let's go over the. So in our class today, we're going to do it in two parts. The first half of the class is going to go over the theory part. It's going to be, I think, it's going to go smoothly and fast. And then in the second half, we'll be go over the Python and work with the example that we were using last classes. And now we're going to apply all these boosting algorithm and see how do they perform compared to our random forest. So far, the random forest was the best model. Now we're going to compare, so we're going to use it as a benchmark and compare it with AdaBoost, GBM, and XGBoost. And we will be considering two things, speed and performance, right? So in both ends, we want to come up with a better model. All right. So as I said earlier, this is going to be our last class for the supervised machine learning model algorithms that we're covering. So we are here in the tree-based models in general. So we talked about decision trees, and we said that these guys are going to be thought as weak learners, and we're going to use them as weak learners to bagging, boosting, and bagging, random forest, and boosting, right? So last class we talked about bagging and random forest. And now we're going to talk about boosting. So we'll be starting with I'm going to remind you what is the difference between bagging and boosting one more time, and we will see what are the terminology in boosting itself. Okay, so in part one, again comparing bagging and boosting, going over AdaBoost, gradient boost, and XGBoost. Just be aware that I'm not going to talk about the mathematics behind it. I'm going to, because this is a lot more advanced than what we did in the class, and it's not going to be, we need at least 2 or 3 sessions to completely cover the mathematics behind AdaBoost and gradient boosting. So for that reason, I will briefly introduce these models to you. I think you're going to have a good understanding of the difference between these models after the class today. When it comes to the optimizing the hyperparameters for these models, you need to know the theory behind these models a little better. So I'll leave it to you. For example, you're working on a project and you throw a bunch of machine learning models at the data. You throw data at those models, and then you want to use XGBoost and see how it performs compared to your existing models. If that's the case for you, you have to dig deeper. I provide a lot of optional readings in the notebook, so please, take your time and do yourself a favor and learn XGBoost, because this is a very powerful model. Then finally, we will be talking about pros and cons of the XGBoost in general, because we know that among the boosting models, XGBoost is going to be the best. Okay, so let's start with the part one. As a refresher, so what was the difference between bagging and boosting, right? So we said that bagging consists of creating many copies of the same data, of the training data. Let me minimize mine. So here we have a data set, let's say this green thing here. So this is our original data set, right? We will be working with different copies. These are different bootstraps of the same data set, right? And we will be applying a weak learner, let's call it WL, to each of these data sets, and each of these models, each of these weak learners are going to come up with a prediction. We'll give you a y hat, right? So in machine learning, we're predicting the whole function, right? So f hat 1, f hat 2, and etc. And we said at the end of the day, we have capital B letter of these f hats, right? Because we are bootstrapping B times. This is capital letter B trees out there, right? And then the output is going to be, if it is regression, it's going to be the average of the F hat. If it is classification, it's going to be the majority vote class, right? So this was the idea of bagging. And then we, well, actually, let me show you this plot again, bias versus variance trade-off, right? So this is our bias square, this is our variance. So we said that bagging tried to reduce the total error by attacking the variance, right? By doing bootstrap, by working with many copies from the same data, we are able to reduce the model variance. And overall, the hope is that you're going to add a little bit of bias to the model, but reduce the variance a ton. So this is how the bagging models are going to attack the total error. So we go from right to left. In boosting, however, we're going to start with the very small, and here we have complexity, right? So in decision tree models, complexity can be thought of as number of terminal nodes or branches, and whatever makes sense to you. But usually people look at it at number of terminal nodes, right? So we start with the very small tree. If I start with a very small tree, and yeah, we start with a very small tree. We know that on average, the model is off in terms of bias. So bias is going to be high. But the goal is to, by making sequential improvements over the initial trees, we will be reducing the bias a ton. So again, the boosting is going to attack this bias variance trade-off from the left. We started from a very small tree. It's only, for example, in AdaBoost, there's only a stump, one tree with one branch. And in the gradient boosting and XGBoost, we can go, we can work with the larger trees, but not that large, right? Maybe 3-4 levels. Okay, so I hope that you get the big difference between bagging and boosting. Just both of them eventually will be able to reduce this total error, and maybe by doing the hyperparameter tuning, you should be able to get a good balance of between bias and trade-off, right? So that's a big picture, a big difference between bagging and boosting conceptually. Okay. All right. Then boosting, as we said, it consists of using the original data, and then we're going to train the data in a sequential manner. So we're going to do this process iteratively. So basically means that let's work with the first weak learner, and the weak learner is able to explain some part of F hat. So we're going to call it F hat 1 again, right? It's going to explain some part of the variation in your data or whatever it's making prediction. And whatever is not explained is going to be passed to the next data set. So your next training set is not going to be the same as the first training set. It's not a small variation. It's completely different. It's different in the sense that you're working with residuals now. You're not working with the original training data set. Does that make sense? So when you look at the target variable, these are not the y hats or subsample of y hats or bootstrap version of the y hat. These are residuals. Okay. So and then we passed this is a second weak learner. So guys, remember, in weak learner, by weak learner we mean decision trees. In ensemble methods models, usually the best weak learner out there is decision trees. But I'm gonna add. There was a question I think Grayson asked that. Is it the case all the time? So can I apply boosting to different models rather than decision trees? The answer is yes, right? But we're going to talk about it, why decision trees are proven to be the best weak learners out there. And then the second weak learner, whatever it's able to predict, we call it F hat 2. And then what's not able to predict, pass it to the next learner. And then maybe this is our F hat, whatever, let's call it capital B, right? So the big difference between bagging and boosting is here. So I want you to pay very good attention. In bagging, we are using bootstrap. So we are using different variation of the data, the entire data set, right? In boosting, we don't do bootstrap. So maybe the names are a little confusing because when you hear boosting, you expect to see bootstrap, but in boosting, we do not do bootstrap. You start with one data set, and then we sequentially grow that tree that we're working with, right? So that's one data set. The features are going to be the same. The only thing that changes is the target variable. Instead of y, you're going to work with residuals at each step, right? So that's one big difference. The other one is that the other big difference happens at the aggregation part. So in bagging, because all these things, look at that. I have one learner that worked with the entire data set, the variation of the data set, another learner, and etc. The aggregation happens as an average, right? Average of F hat 1, F hat 2, F hat 3, and etc. But in boosting, the aggregation happens in an additive manner. So what does it mean? It means that whatever the first model was able to predict, then I'm going to add with the shrinking parameters. This lambda is called shrinking parameter. The predictions from the second model, then add the predictions from the third model, and etc. So it's additive. You're not taking the average, right? And as you can expect, maybe this has a larger contribution to the final predictions compared to the second one. We're going to talk about these tuning parameters. Does this make sense? Do you see the big difference between bagging and boosting? So these are the two big differences. In bagging, you're using bootstrap. In boosting, there is no bootstrap. Again, and the second difference in bagging, the aggregation is, we look at it as an average of the predictions. In boosting, it's we do it in an additive manner, right? So you add it by using some shrinkage parameter. Yeah.
I might be thinking about this in the wrong way. Do we run into any issues with collinearity across the models and boosting, since we're basing?
Well, collinearity, you mean if, for example, if you have very, very highly correlated features in the data.
Yeah.
In general, decision trees are able to handle the collinearity a lot better than the other models that we cover. And but if you are thinking that if these models automatically delete collinearity, the answer is no. Actually, it's a very good segue for us to do the principal component analysis in next class, because maybe you have thousands of features and you know that hundreds of them are collinear, so you want to reduce the dimensionality by a lot. So you would be better off if you apply principal component analysis, get rid of all those collinearities, and then apply any of these supervised machine learning models. Does that make sense? So this is, but that was a good segue for our next class. But these are not designed to get rid of those collinearities. So you can, so that's the negative side. But the positive side is that they can handle it. Okay, it's not like, for example, even if you have perfect collinearity, these models can handle it. Okay. By handling it, I mean that it does not get rid of it. It can survive. It can give you predictions, right? We know that, for example, in our simple OLS, if you have perfect collinearity, OLS cannot do the job. Okay. So now let's start with AdaBoost. So for AdaBoost, GBM and XGBoost, I put together only one slide, but I think, again, the hope is that you get the big picture of all these models. If you're interested in the mathematics and the theory behind it in more details, I've provided more extra links for you. So let's start with AdaBoost. So this is this was the vanilla version of the boosting method out there. And it's basically, the idea is that it's a forest of weak learners, and the weak learners are stumps, right? Stump means that it's a tree with only one feature. So this is a stump, right? This is a forest of all these stumps. So, and then sequentially, and guys, remember, this is done sequentially. So we start with the first stump, and then we save the residual, not the residual. Well, let's talk about AdaBoost. Let's see how it's done. So in each tree depends on the previous tree's error rather than being independent, right? So let's say this is our data set, and we're going to start with the first stump, right? Box 1 is our data set. So what is the first step? We are going to start with our usual splitting criteria, right? So imagine this is classification. We have a blue crosses, and then blue plus and red minus, right? So this is our data. Imagine this is a classification data. And if you want to start with the first box, we have two options in terms of coming up with the splitting criteria. Maybe, so I have a vertical split and I have a horizontal split, right? And in classification, what is the criteria? How do I know that if the vertical is better than the horizontal? You remember? How does a decision tree, simple decision tree, decide which split to pick? You have to look at some impurity index reduction, right? So we have to calculate the Gini index or entropy or whatever, right? So I leave it as an exercise for you. If you go ahead and calculate the Gini for this split, I did the numbers. You should get, for the horizontal, you should get, for the vertical, you should get a Gini of 0.375. And for the horizontal one, you should get a Gini of, this is a good exercise, even though you're not required to do these things manually, but I encourage you to do that. So if that's the case, which one is the better split? The better split is going to be the vertical, and the algorithm is going to start with that, right? So in AdaBoost, we start with the usual splitting criteria. Remember, it's a very, very small tree. It's a stump, just one split. The algorithm does one split, and what is the next step? It's going to give each tree or each stump different weights, right? So the output of the first tree is going to be an F hat, right? Let's call it F hat 1. Based on the accuracy of this tree, it's going to give it some weight. Let's call it weight 1. Are you following? So I can compare the accuracy of this one, box 1 versus box 2 versus box 3, right? So, and I can give them some weights with regards to the accuracy, right? Then each observations themselves, so each instances will get different weights as well. So what does it mean? The weights is going to be inversely related to its prediction outcome. So what does that mean? For example, if I look at this first split, the blue ones, these are awesome, right? These are good classification. The ones on the right, these are bad classifications, right? These are misclassified observation. So the algorithm is going to give them more weights, right? Why do you think that's the case? Why it's giving it more weights instead of less weight? Remember the big picture of the boosting. It's going to work on the errors, right? So AdaBoost is going to give more weights to the misclassified observations instances, and then it's going to highlight them for the next tree. And conceptually, how does this giving more weights to the observation happens? It's going to repeat them more in the data. If you have 10 observations, 3 of them were misclassified. In the next tree, those 3 observations are going to show up more. So if they show up more, they're going to have higher impact in terms of making the prediction. Does that make sense? Okay. So it's going to highlight these 3 pluses, blue pluses, and this is visually something like this, right? You see that the size of the pluses is bigger. But remember, mathematically, conceptually, it's done by selecting more of these observations in the data. Okay. Then the next, so this was our, let's say the first step, the first weak learner. Then we go down to, we work with the second weak learner, right? So in the second weak learner, the algorithm is going to, and when I say algorithm, it's our simple decision tree. It's going to focus more on these plus sign. And then if that's the case, it's going to come up with this split. So this is going to be the second split, right? And then this box itself is going to have a weight itself based on its prediction. Again, this process is going to repeat and repeat and repeat. If that's the case, then it's going to give more weights to these guys, right? Do you agree that these are misclassified now? Okay. So it's going to give them more weights. If it gives them more weights, the next split is going to be something like this. Are we good? Then we have, for example, F hat 3 and W3. Okay. So now we know that, just remember in AdaBoost, there's 2 weightings going on. For the first weighting is for the decision trees themselves. And the second kind of weighting is for the instances, for the observation within each tree. So this is a big difference between AdaBoost and other boosting methods, right? In AdaBoost, observations themselves are weighted. In GBM and XGBoost, all the observations are treated similarly. The weighting is different. Okay, cool. And then this is the aggregation. So if you aggregate all these splits, we come up with this model. This is our AdaBoost. And as you can see, it was developed sequentially. We just added to that tree one by one by one. So this is a really neat algorithm. I hope that you can see, at least you can enjoy the beauty of it, how it's done. Okay, aggregation is done based on each weak learner's weight. So this is how we aggregate things. Based on weight W1, W2, W3, we come up with different, we aggregate them over. It's simply like taking an average, right? Okay, so that was the AdaBoost. Is this clear? Is there any question about the AdaBoost? Guys at home?
So you combine the 3 weak learners to make one.
In this example, yeah, it's 3, but in general, capital letter B, yeah, we will end up with thousands of those trees, thousands of those boxes here. And each of those trees are stump.
But is there?
One simple split.
Is there overfitting issues when it does that?
Well, in boosting in general, yes, you can definitely overfeed with boosting, but there are hyperparameters that you can tune. Yeah, it's a good point, Abraham. Boosting in general is more exposed to overfitting compared to random forest bagging. That was a good observation. Okay, but again, we can get rid of those overfittings by hyperparameter tuning, or basically adding regularizing the model, which this is what XGBoost does. Now, the second boosting method is GBM, gradient boosting machine. And in gradient boosting, each weak learner, remember the weak learner is again a decision tree. Correct its predecessor's error. So the idea is the same. So it's going to focus on the error of the previous tree, right? But the difference is that unlike AdaBoost, the weights of the training instances are not tweaked. So this is the big difference that I was talking about in the previous slide. So in AdaBoost, we are giving these observations that are misclassified different weights. In gradient boosting, we don't do that. Oops. Okay. Let me just exit and come back again. Let's see. Okay. So each predictor is trained using the residual error of the predecessor as labeled. So here's the difference between the two. Imagine this is, I think it's easy to see what's going on with the regression. And then for classification, the idea is the same. So this is your first training data set, right? And you're going to build a tree on top of that. And by the way, why this one doesn't work? Yeah, another difference between the AdaBoost and the GBM is that we can work with larger trees than a stump, right? So this can be a tree with, this can be something like this. It's not necessarily a stump, right? You can go 2 levels, 3 levels, right? I think in practice, we don't go more than 4 to 8 terminal nodes. You try to keep that tree very small because it speed up the process, and we'll talk about it that why those trees are, the initial trees are going to be small. Okay, but whatever it is, we're going to apply this simple weak learner to the data, to the train set, and then we come up with some predictions, right? So these are the predictions from the first weak learner. Then you calculate the residuals. So what are residuals? Y minus y hat. You calculate the residual and save them. So these are the residuals from the first tree that we're applying to our entire train set. Okay. Then look at that. So here's the difference. We are going to pass the same features, but now instead of y, we're going to pass only the residuals. So the part that has not been explained. Okay. And then apply another tree, and then move on and save the residual. So residuals are going to be r minus r hat now, because these are the residuals. It's not the y minus y hat anymore. And then same story, right? X and R2, calculating R3, and here we have n minus 1 of them, or you can think of it as capital letter B. All right, so we are doing this thing sequentially over B of these trees. Okay. And finally, so what is it? What are the predictions? So for example, here we have f hat plus we have lambda. Well, if I want to use the same notation here, I have y hat plus lambda, not y hat, right? We have residuals, right? Residuals 1 plus lambda, residuals 2, and etc. Does that make sense? So this is how the GBM is doing the predictions, adding all these things. This was for regression. For classification, the story is exactly the same. So here in gradient boosting and XGBoost, the outcomes of the classifications are probability. So these are not classes, 0, 1, 1, 2, 3. These are probabilities. And so for that reason, because we're working with probabilities, the methods are going to be the same. Okay, so we look at MSE, mean squared error. We look at, there are different versions of MSE. In Python part, I'm going to talk about it, right? So we are going to work with numbers. Probabilities, 0.1, 0.2, 0.3. Okay. So learning rate shrinks the contribution of each tree. So this lambda is what we call learning rate, right? I think it's the concept of learning rate is pretty standard. It's basically the tell you what is the contribution of each tree, and it's going to give the same weight to all the following trees. Lambda. It's not lambda 1, lambda 2, lambda 3. For all the following trees, it's going to give them one weight, right? There is a trade-off between learning rate, lambda, and number of trees. So if the learning rate is smaller, what happens to number of trees? If you want to get, for example, the same accuracy, not same accuracy, you want to get more accurate model. So if, yeah, it goes up, right? So if lambda is small, then the number of trees should go up if you want to get this relatively same accuracy out of the model. If the lambda is large, so the outcomes are going to converge faster. Does that make sense? Okay. So that's a trade-off. So learning rates slow down the process even further, allowing for more and different shaped trees to attack the residuals, right? So in practice, it is better to work with the smaller lambdas and give the gradient boosting machine more time to attack the residuals with using different trees, right? Because guys, remember, these are small trees. What if I have thousands of features and in each tree, there's only 2 or 3 of them are going to show up. So for that reason, you want to make sure that each of these trees, each of these features have a chance to show up in the final model. This is different from random forest, right? Random forest usually start with a larger tree. And this picking a subsample of the feature set is happening at each split, right? But here, because these are very small trees, you need to make sure that all the features have a chance to show up in the model. So for that reason, lambda should better be smaller. But if lambda is smaller, so what's the caveat? What do you think? Yeah, it's going to take longer. This is exactly what XGBoost is going to attack, right? So GBMs are in general very, very slower than XGBoost. And these terms are relative. When I say very slower, you're talking about, well, XGBoost is super fast. So that's why now relatively we say that GBM is slower. But these are fast. In general, if your sample size is small, all of them are the boosting methods are very fast. And the bagging methods, both of them. Aggregation is done by adding the first tree predictions and the scaled version of the following trees. I think this makes sense, right? The scaled version means that lambda multiply that and lambda. So y hat plus lambda will multiply R1, R hat 1 plus lambda multiply R hat 2, and etc. That was the GBM. Is there any question? Is it the difference between GBM and AdaBoost clear? Yeah.
Is capital B a hyperparameter, or is that?
That's a hyperparameter. Yeah, that's a number of trees that. Well, this is sequential. Let's go back here. Capital B here is the number of bootstrapped trees, right? So here in the bagging, it's a number of, again, trees, but sequential. It's not, it doesn't go over the entire train set, so it's going to work on the residual of the train set. But yeah, that's it. Basically, it tells you how many trees you're going to end up with. Okay, now finally, let's talk about XGBoost. So why the XGBoost is the winner of many competitions, and why it actually revolutionized the hope in machine learning world in general, right? Because I think we talked about it. If you go back 5 years ago, when you look at the Kaggle competition winners, if you look at the M series competition winner, most of them were statistical learning models, right? Either ensemble or standalone models, right? We can do ensemble methods to statistical learning models, right? So work with a combination of the statistical learning models, take the average and call it combined models. But recently, if you go to I don't know, if you look at the competitions from 2016 and onward, all of them overwhelmingly, the winners are a combination of machine learning and statistical learning. Especially in forecasting, statistical learning is still super powerful. But in making predictions like this, I think the neural networks and XGBoost are the winners, or the absolute winners. So why that's the case? Let's talk about how XGBoost was developed, and we're going to do it in one. We try to do it in one slide, and let's see what's the fuss about, right? Why we are so excited about XGBoost. So the XGBoost is a redefined and customized version of the gradient boosting. So it's not like AdaBoost. It's like GBM, right? And remember, what was the difference between AdaBoost and GBM? it is created with having performance and speed in mind. So performance when it comes to accuracy, and speed when it comes to calculation speed, right? And in my opinion, it's going to improve. So at least based on my experience, usually the performance of XGBoost and random forest are close to each other. So people are going to work with XGBoost because it's super fast. And we're going to see what do I mean by super fast, right? But for many finance applications, I personally didn't find huge improvements of XGBoost over random forest, but that's probably because of the nature of the data. So in different fields, maybe that's the other story, or the nature of the data that I work with, right? If I work with maybe higher dimensional data set, XGBoost is going to do a better job. Okay. So, and this X in XGBoost refers to extreme, and extreme refers to the fact that the algorithm and methods have been customized to push the limits of the gradient boosting methods. Let's see how XGBoost is able to do that. Let's start from the right-hand side. So these are the advantages of XGBoost over GBM in general. So starting with the first one, there is this inbuilt cross-validation capability. So this is very, very genius. The idea is that instead of training the model and then going back and tune the hyperparameter using cross-validation at each tree, at each boosted tree, not bootstrap, boosted, right, at each sequence, it's going to use a cross-validation and then the update the parameters or hyperparameters at each boosted tree. So this is all done inbuilt. Well, you don't need to do it manually. The second one, it's efficient handling of missing data. So remember, to reduce the data sparsity, it's a big deal, especially if you start dealing with the terms of dimensionality, and we know that the data is going to become sparse in higher dimensions. Then handling the missing variables is a big deal, right? And the XGBoost automatically is going, and efficiently, so the key term is efficiently, is going to handle the missing data for you. You have to provide some inputs for sure, but it's going to do it automatically for you. So the next one is regularization to avoid overfitting. So this is a big advantage of XGBoost over GBM and boosting in general. The idea is that, and we're not talking about the standard regularization parameters that we saw even in simple decision tree, right? I'm not talking about, let's say, maximum depth of the tree or minimum number of terminal nodes or things like that. I'm talking about something like this. So in boosting, we have a loss function, right? So the objective function in boosting, I showed with objective function in boosting and bagging in general, something like this. We're summing some losses, and the losses are a function of y minus y hat, right? Well, let's call it y and y hat because it's either classification or regression. So this is the general shape, the general form for the bagging and the boosting GBM, right, or AdaBoost. What XGBoost does is going to add a bunch of these, let's call them omega, and omega is for regularization term. I call it the regular term, and it's a function of complexity of the tree, right? So if the number of terminal nodes is high, and this regularization term is unique to XGBoost. So this is what XGBoost does on top of gradient boosting, right? And you can apply L1, L2 norm, or any other kind of customized version of this regularization functions, and the inputs are the weights of the terminal nodes, right? So each terminal node is going to have a weight, and if I have more terminal nodes, it's going to penalize it either by L1 or L2 norm, right? So that's the beauty of it. So it's going to do this regularization to avoid overfitting. So it is, you can play around with the parameters for the regularization and then come up with less overfit model. So that's another thing. Then the next one is cache awareness and out-of-core computing. So this cache awareness and out-of-core computing, this is a technical thing, and which is going to speed up the process. So the part that's the XGBoost is going to do a lot faster is happening here. So what is the idea of this cache awareness? We know that CPU, the computer CPU, is the fastest on cache memory, right? And then it's going to be, let's see. Yeah, it's fastest on the cache memory, and then it's going to be faster in the main memory, well, less fast in the main memory, and then the hard drive, right? So XGBoost is going to do the calculation in cache memory. So this is a big advantage of that, right? And so that's called cache awareness. And out-of-core computing. So out-of-core computing stands for how XGBoost is able to utilize extracting information from the hard drive, right? Because we know that if you want to write and read from the hard drive, it's going to take a lot of time. So XGBoost, what it does is that it's going to decompress the data, and then it's going to from the hard drive. So this decompression is going to take a little time, but when it's decompressed from the hard drive, it's going all the calculations done in the cache memory. So for that reason, it's going to be a lot faster, right? So this is what we call out-of-core computing. Okay, so cache awareness, everything is done in the cache memory, and core computation is going to not reading from the hard drive. Because guys, remember, with the data sets that we are working, it's no big deal. But large data sets, we're dealing with terabytes of data, right? Unprocessed data. So it's going to decompress them very fast, and then bring it up to cache memory. So this is where the speed is happening. And the next one is true pruning using depth first approach. So what is this one? So gradient boosting, remember, it's still working with that greedy algorithm. So think of the sequential process. Imagine you're the GBM and you want to start with the first split, and you're working with a very small tree. And you're very greedy. If you get the best split, you call it split and then move on to the next tree. So it's as if you're ignoring the better potential splits down the road, right? But XGBoost is using something called tree pruning using depth first. Depth first method is, or search method is, go all the way down on the tree, look at all the splits, and then prune back. So this is how XGBoost is doing, right? So this is going to be a lot better than the GBM, because GBM is greedy. Well, it's less greedy than AdaBoost, but still it's greedy. It worked with the best split and then go to the next tree. But the XGBoost is the search for the split is going to be based on this depth first approach, and that means that go all the way down and then prune it back. Okay. Finally, parallelized tree building. So again, this is another part that is going to do a lot with this computation power, speed of the computations, right? And I think we talked about this one, that the random forest is also parallelizable, if you wish, but XGBoost it's going to do everything in parallel automatically. It's not parallelizable. It's already doing things in parallel automatically. And the fascinating part about XGBoost compared to GBM is that, guys, remember, these are sequential models. It means that you have to go to the first tree and go to the next tree and then go to the next tree. How on earth are you able to parallelize this process? So this is very genius, right? So that's beyond the scope of my understanding personal, because it has computer science, it needs computer science background. But think of it intuitively. These are sequential models. So AdaBoost and GBMs cannot handle parallel computation because of that. These are sequential models. You cannot break down the data and then pass it to the model like this. But XGBoost, even though it's sequential, it can handle that parallel computing. Are you following? Kinda? Okay. So I think I was trying to show you the beauty of the XGBoost, right? The mathematics behind it is, of course, a little more challenging. But that's why the XGBoost is doing fantastic when it comes to computation speed. So let's look at this data set. This is a hypothetical data set that comes with the scikit-learn package. We're working with this is 1,000, right? Well, 1 million randomly generated data samples with 20 features. So the dimensionality of the data is not huge, but the data itself is, we have 1 million observations, right? And we are comparing this is AUC, or area under the ROC curve, whatever, and versus the training time. So this is the speed, right? As you can see, logistic regression is very fast, because this is a parametric model without any hyperparameters. So it's going to be fast. And but look at the accuracy. So the accuracy is going to be 93%. Well, this is area under the curve, not necessarily accuracy. Let's call it accuracy, but you see let's call it AUC, right? The AUC is 0.93. Random forest, of course, is more accurate, and then gradient boosting is more accurate. XGBoost is more accurate. So you're not surprised that GBM is doing a better job, relatively better job than random forest. And random forest, this is definitely not surprising that it's going to do a lot better job than the logistic regression. But guys, look at the numbers. When I say a lot, it's only 2%. But remember that, remember Netflix paid $1 million for, I think, a couple of percent increase over the accuracy, right? So this is a performance, this is the speed, and this is where XGBoost shines. It's a lot faster with the same level of accuracy. So that's if your data set is small, you would end up with a good accuracy if you use random forest or GBM, and it's going to be fast enough. But if you ever work with a huge large data sets, your answer is going to be XGBoost, right? Okay, and yeah, I think we talked about the development of the tree-based models. So this is decision tree versus and then you start with decision trees and then use them as a weak learner in bagging, and then random forest, and then boosting, GBM, and then XGBoost. So where are we today? Today, the Microsoft, as I said earlier, Microsoft Light GBM. I think it was introduced January 2016. It was the first stable version that came out by Microsoft. And then AdaBoost. This came out, it was in April. Oh, this is 17, sorry, not 16. 17. This came out a couple of months later, April 2017. When it comes to performance, I think XGBoost, Light GBM, and AdaBoost are relatively the same. And XGBoost usually outperform if there are not many categorical variables. But if there are many categorical variables, at least the consensus in this literature suggests that AdaBoost is better. But when it comes to speed, these two are faster. Because the process of, especially Light GBM, what Microsoft offered, because the process of finding the first split is genius. There's a method that Microsoft proposed that was very beautiful. It was even more beautiful than XGBoost. But again, if you're interested, I provide some links in the notebooks. Just go ahead and give it a try and see if that's something that interests you. But at least you should know what's behind these models and where we are standing as of 2021. Okay, pros and cons. So pros, these are the advantages of XGBoost. What are the disadvantages? Not surprisingly, it should come with a cost, right? What's the cost? There are many hyperparameters to tune, right? So if you want to tune the hyperparameters, and if you're, it depends on what data set you're working with. But if you want to make, first of all, if you want to make sense of all those hyperparameters, you have to know what's happening behind the scene. And secondly, there's a lot of them. There's a lot of them. Okay, so you have to do a random search to do the optimization. And all these things are becoming more and more automated as the computation power is going to increase over time. Okay, now let's go to the students' questions. Is there any question about AdaBoost, GBM, and XGBoost? You're good? Are you excited about these models? Are you happy that we had this class or no? Because I was kind of debating with myself that is it the right fit or not, but you let me know, okay? We didn't cover any mathematics, but still, we understand what's the difference between these ones. Okay, let's go over the students' question, and we're going to quickly cover the Python part. Number one, I'm still a little unclear on what exactly boosting is and how it differs from bagging. Are we good on this one? Okay. Is boosting just a decision tree thing, or can the same technique be applied to other models? What's the answer? What do you think? Basically, can I use ensemble models? Can I use any other model than decision trees for the boosting process? Even simple regression, the answer is yes, right? We can. But it turns out that decision trees are the best weak learners out there. So weak learner decision trees are best weak learners out there. Why? Why do you think that these are the best weak learners? Because remember, do you remember we talked about interpretability of decision trees? These are the most interpretable weak learners out there, right? If you keep it small, you can easily see what's going on. So that's one reason. Another reason is that the decision trees are non-linear. And usually the sequential models are not good with, does not work good with a linear model. Why? Because remember, guys, if you're doing something in a sequential manner, there's a chance that a feature, let's call it X1, is going to show up in multiple times. If X1 shows up multiple times in a sequential manner, it's going to be non-linear. If your model is linear, it's not going to be a good candidate for your weak learner. So this is another reason that why decision trees in practice are the best weak learners out there. And another reason is that decision trees are super fast, especially the small ones that we're, so think of AdaBoost or XGBoost. These are, we're working with very small trees. These are fast, right? So for that reason, this is another reason that why decision trees are the best weak learners out there. And lastly, by changing the depth of your simple decision tree, you can easily balance the trade-off between bias and variance, okay, compared to other models, right? For example, in simple KNN, you have to do the whole thing and then find the K, which minimize, for example, like maximize the accuracy of things or minimize the RMSE. But in simple decision tree, you can keep the tree very small and then or change it a couple of times, and you can easily play around with the trade-off between bias and variance. So for that reason, decision trees have been proven to be the best weak learners out there for ensemble methods in general. So, but the answer to this question, the answer is absolutely yes. You can use this boosting method. This is a general purpose method. Boosting and bagging, both of them are general purpose method. And the goal is to increase the accuracy for both of them. Why would you use something other than XGBoost? Very good question. What's the answer? We talked about the caveats of XGBoost, right? So if you're a non-expert, the tuning parameter is going to be difficult. And yeah, in many applications, in many projects that I personally work with, I think our simple random forest is doing a good job. I like random forest a ton. And if I'm not concerned with the big data, I prefer random forest because in my opinion, the feature importance of random forest is more stable than XGBoost. But this is something that we're going to talk about it in the Python part. But again, this is my opinion, it can be wrong, but at least according to my whatever data set that I work with, right? And I think whatever I say today in 2021 is going to be proven wrong or improved in a couple of years. This is just a matter of time. Right? We're improving these models. So, for example, I think there was another question in the quiz that why do we need to even improve the XGBoost? The answer is speed. The amount of data that we can handle and process these days is insanely higher than just 6 months ago, So we have to come up with models that are faster. And this is exactly what like GBM and XGBoost are doing. What is the additive model utilized by gradient boosting? I think, I hope that you got the answer, right? The additive part, because we are doing a sequential, we are doing the boosting idea is sequential. So we are adding the predictions at each sequence, right? And the next one is going to be added to the first one by using a shrinkage method, a shrinkage parameter. That's it. Okay, so let me stop share. And this was the first part. If there is no question, let me go ahead and share my screen to go over the Python part. The Python part is going to be fast. Is there any question from the theory? Good. Okay, let's go over. Everyone see this screen? Let's go over the Python part. So there is this, and I have done it only for classification. I leave it as an exercise for regression. So this is your next homework 11, which is due this Friday. I already got a couple of emails that it is way back to back. We are overwhelmed. We have Monday homework due and then Friday. I can push it back, but give me 20 minutes until the end of this class. You will see that homework 11 is piece of cake. Okay, so it's an extension to our homework 10. So I hope that you can really do it in half an hour or even less than that. All right, so let's talk about how we can implement all these things in Python. And by the way, AdaBoost and GBM comes with scikit-learn package, but XGBoost itself is a, it's, well, we're going to get through that. I want to make sure that I use the right term, but when it gets, it's not a scikit-learn thing. It's not a Python thing. It's not an R thing. It's a package for itself, which can be implemented in R, Python, Java, whatever you name it. And the speed is going to be the same. So it really doesn't matter if you apply it using R or Java or Python. Okay, so we are going to continue our study. We were working on this credit card well, not credit card data set. We cleaned it up in homework 3, and then we are continuing working on it. And this is a data set that we got from the Kaggle competition, the credit card data set. So I think we're all familiar with this, with the data set. Let's see. Yeah. So at the end of the day, we want to predict if this person with these properties, with these features are going to default or not, right? And if you remember last time, we saw that if I use random forest, pay one was the most important feature based on random forest. And that made sense, right? Because what is pay one? It's basically your repayment status in the previous month, if you paid it in full, or if you are just lagging some payments. Then the data is very clean. We don't need to be worried about it. So let me go to the part which is related to our class today. Again, we ended up making sure that the categorical variables, oh, I didn't talk about it in the theory part. So the categorical variables in the random forest and GBM, you have to make sure that these are numerical numbers, numerical values, right? So if you have married versus single, so you have to make sure that married is 0, single is 1, and etc. Right? However, AdaBoost and like GBM, you don't need to be worried about that. Maybe you think that it's no big deal, but imagine a word that you have, I'm not kidding, millions of features. And then you have to, let's say you have to change 100,000 of them from letters to numbers, right? So again, just to scale, try to, whenever you're thinking of all these improvements, just to scale it up in your mind, right? Don't think of these simple examples, just to scale it up. Okay. And scaling the features. You don't need to be worried about it. This data is relatively balanced, and then let's go ahead and construct our train and test. So this is the target variable default. Then everything else is going to be our feature space. Okay, so boosting classification using scikit-learn, and I'm going to import the random forest as a benchmark, right? Because I want to compare the performance of the boosting models with the random forest, and then I'm going to import also AdaBoost classifier and gradient boost classifier from the scikit-learn ensemble class, right? For your homework, you can simply just import 4 of them or 5 of them together. AdaBoost classifier, AdaBoost regressor, gradient boosting classifier, gradient boosting regressor, and random forest. However, for XGBoost, guys, remember, XGBoost itself is a software library. You can download it and install it on your machine, and then you can use any of these interfaces. C++, Python, R, Julia, and Java. Okay, to install XGBoost in Python, so you can just type in this in your command line, or if you're using Anaconda, just do Anaconda prompt and then type it there. pip3 install something like this. I do cmd, not the cmd. Just do pip3 with no space. pip3 install XGBoost. So this is the university computer, because we didn't, when we were installing, I think, Python on this one, we didn't add the path. But on your computers, if you have installed the Python the way that I told you, you should be able to do it there. If not, just use the Anaconda prompt and then type this pip3 install XGBoost there. Okay. And if you get, if you're faced with any kind of errors, just read this documentation from the XGBoost. Okay, now that I have installed the XGBoost, I can import it. I can import XGBoost classifier. Oh, I see. This is my office computer. So let me, because in sake of time, let me continue this without running the lines. You'll see the output anyhow, right? But because this is my office computer, and I don't have installed the XGBoost on my computer. I will see if you have time. I'll show you how to do that. But other than that, so imagine this line has been run properly. So we have XGBoost up and running. Now we're going to train the model, and I will train 4 of them: Random Forest, AdaBoost, GBM, and XGBoost, right? So we're going to train them with their very basic inputs. But in order to make sure that this is a fair comparison, apple to apple comparison, I'm going to set the random state to equal to 1000 for all of them. This random state is 1000. We define it up there. And look at the time. Random Forest 3.97 seconds. The AdaBoost 1.31. GBM 11 seconds. And the XGBoost 1 second, almost 1 second. So it's going to be a lot faster, at least than the GBM. And we're going to compare the accuracies as well. So random state here. However, for GBM, again, because in order to make sure that we're comparing apples to apples, we're going to work with learning rate. This is our lambda, 0.1, and max depth 6, because this is a default number in XGBoost. I just put these 2 here to make sure that we are comparing apples to apples when it comes to GBM and XGBoost. And learning rate is the same as eta or eta in XGBoost package, right? So the author of the package, well, the software decided to call it eta. Okay, and then as you can see, there are lots of other hyperparameters to be able to tune. So, and then we're going to make predictions. So I'm going to call it y hat rf, AdaBoost, GBM, XGBoost. This part is very easy. You know how to make again. We train the model in the train set. We make prediction on the test set. Now let's evaluate the model. So for evaluation, we're going to do. We're going to look at the accuracy score, recall, precision, or an F1 score. So in this, I think here I just show you the F1 score. Why? Because the data was relatively imbalanced, I believe. Well, it's relatively balanced. It's okay. I can do accuracy or F1, but just we can compare F1 score here. And then let's see how they work. And then you can look at the confusion matrix or use that built-in classification report, RC curve, and etc. So for your homework, I just want you to do something like this. You know, simply compare the random forest with all the 3 boosters and then report these numbers. That's it. So your homework 11 is super easy. So again, if you want, we can push back the deadline, but I'm quite positive that we can do it. So when it comes to the performance of the model, look at that. The random forest accuracy is 82%, AdaBoost 82%-ish, GBM 82, and XGBoost 82. So they're very performing similarly without any hyperparameter optimization, right? So now you can play around with the inputs of the random forest, AdaBoost, and GBM, and well, actually, let's talk about them a little bit. Let me look at this contextual help, because I'm sure that many of you are going to end up using XGBoost or GBM. So let's talk about some of the hyperparameters here. So this is our random forest. We're quite familiar with all these things, right? We know what is Gini, with number of acids. This is the capital letter, capital B, max depth, and all the regularization kind of parameters here, right? And so this is our random forest. For AdaBoost, remember, we were talking about stump. So if it is a stump, I don't need to be worried about the max depth, max number of leaves, and etc. Right? So we are not going to end up with these things, with this one in the middle. But still, there are some parameters that we can tune. This is our number of estimator. This is B, learning rate 1, and algorithm. Again, you can read through the documentation and see what does it stand for. But I think I did it. Algorithm. Yeah, I see. So if this is your target variable is continuous or discrete. So if it is continuous, we can use this one. If it is discrete, we can use the other one. And then for gradient boosting, so this is the one that you I don't want you to do it in the homework, but you can play around with that. So if you want to optimize the hyperparameters for the boosting, for the gradient boosting, you can do grid search cross-validation, right? In grid search cross-validation, you can play around with the learning rate, you can play around with the B, and then criteria. What else do we have? And this is our cost complexity alpha. You see, it has all the features of tuning a simple decision tree. And the loss is deviance, and it's defined as, if you look at the documentation, deviance is a loss function. Basically, it's a logistic regression loss function. Guys, remember, I think I talked about it in the theory part. The output of the GBM, XGBoost, these are probabilities, right? Because it is probabilities, when it comes to criteria, it's not Gini or entropy anymore. It's a version of MSE. So here it's the Friedman MSE. If you go to the criterion part, so we have MSE, we have mean absolute error, and then Friedman MSE. Just read the documentation and see what's the difference between them. But I hope that that makes sense why we don't have, even though it's classification, why do we want only have Gini or entropy? Because you're using this loss deviance based on logistic regression. And so that's for the GBM. And for XGBoost, so let's, oh, because I didn't load it up XGBoost, you don't see the documentation for that. XGBoost has all these things, but on top of that has L1, L2, because those are the regularization parameters and a bunch of other stuff. Okay, I think you can see them here. Yeah, you see, this is our lambda. Do you remember our lasso regression, ridge regression? So we had, so this is the same alpha and lambda in our lasso and ridge regression. And yeah, there's a lot of things that you can tune using XGBoost. Okay. That's pretty much it. So let's talk about the, so in terms of performance and speed, so which one is the winner? If I look at the combination of the two. So here, for example, we have F1 score. Random forest has a higher F1 score than AdaBoost, but GBM is outperforming the random forest, and XGBoost is outperforming all of them. Okay, let's come to F1 score. So which is the winner? Which model is the winner? Of course, the XGBoost, because it was a lot faster and it's more accurate. Has a higher F1 score. Your homework is this. Now, I ask you questions like this, which you have to compare 4 models and then just report back which model is the winner, why. Okay, and you have to do it for classification and regression. So this was only classification. For regression, just import the regressors. Feature importance, the same story. We're going to have. Do you remember how we can do the feature importance in random forest? AdaBoost, GBM, and XGBoost, they all have this feature importance method that they can pick, right? If you do dot feature importance, it's going to save those feature importance values for you, and then you can plot them, right? So here I put together all these feature importance and I rank them based on the random forest feature importance. So for example, let's see, here this is my random forest. So random forest says that the most important feature is pay 1. And so it seems that AdaBoost is, in AdaBoost, bill amount is the most important, and then pay 1. In, this is GBM, yeah. In GBM, it is consistent with random forest, and yeah, in XGBoost, it's also consistent with random forest. So it seems that pay 1 is the most important feature out there. We can plot them. You can go ahead and change these. For example, instead of RF, you can do AdaBoost, and then plot it based on the AdaBoost, the feature importance. Lastly, there is this plot importance feature function that comes with the XGBoost software package. From XGBoost, you can import that plot importance, and then you can pass the model that you trained. So we call it the XGBoost classifier. And I'm afraid that I cannot load up the documentation here, but if you look at this grid, it talks about how differently you want to put weights on how this important feature is selected, right? So for example, gain is based on if it is classification, entropy gain, or Gini gain. If it is cover, it's based on something else. And so it seems that if I use this plot importance from XGBoost, which one is the most important one? Bill amounts in the first month is the most important one in the previous month. And then we have balance limit. We have, again, bill amount, age. Here's pay 1. Yeah, pay 1 turns out to be here. Again, if you use different grids, you're going to get different values for the feature importance. And that's why, so this part is very based on my personal observation. I can be completely wrong, but based on my personal observation, the random forest importance feature is more stable compared to XGBoost. So for that reason, if there's not a huge difference between random forest and XGBoost outcome, I would prefer to report the random forest feature importance. And but regardless, what we can get out of these things. So imagine I had hundreds of these bars here, right? I had 100 features and I had 100. I can quickly look at this information and say, you know what? It seems that, look at that, these variables are very, very highly correlated, right? So, and intuitively it makes sense because it's payment status in the past 4 months, 5 months, 6 months, and etc. And imagine I have thousands of these ones. So what is a good strategy to do is to reduce the dimension of the data, right? And this is what we're going to do next class. We're going to use, for example, one method is principal component analysis to say that instead of working with, I don't know, I'm just making a guess, 20, let's say this is 20 features, I want to work with the most two important ones, right? That are explaining 80% of the variation, explaining 90% of the variation, right? And now I'm able to reduce the dimensionality of the data from 20 to 2. Or we're going to look at an example next class, which is in CFA reading, from 2000 to 3. That's where the beauty of this principal component analysis is going to shine, right? And then when I have reduced the dimension of the data like that, I can use KNN. Do you remember KNN was powerful? It was a non-parametric powerful model, but it was performing very bad because of the curse of dimensionality. So I can apply PCA, principal component analysis, as an unsupervised learning method, and then pre-process the data and just feed the supervised learning with that pre-processed data using PCA. I hope it makes sense, but we will talk about it. So this is again the way that I want to connect what we learn in supervised learning methods compared to unsupervised learning method, right? So especially when it comes to dimensional reduction in unsupervised learning methods, we're not going to use them. Maybe we're not going to use them directly, but indirectly we can use them and feed our supervised learning models with those models. Okay. All right. So what's the time? So we have 5 more minutes left. Let me go ahead and stop the recording, and I'll take questions. I have some comments about the course. Guys at home, do you have any questions? Are we good? Are you still there, alive?
Yeah, I think we're good.
All right. Okay.